Good evening, everyone. It's very nice to have you again for the second class of day one. I'm very happy to introduce the speaker for the talk, which is Kutte. He's from Karad, Maharashtra, and he's currently in 11th grade, and he has an APMO medal, bronze from this year, and he is insanely good at geometry. You can also, like, he's good at everything, but he's really good at geometry and combinatorics, and you can check out his fun sessions that he's taken some nice classes on OMC. You can just look them up on YouTube, and it's super exciting that he'll be talking about Inversion and Projective today. Yeah, I think that's over to you. Thanks a lot for taking this class. Oh, he's also an organizer. I'm also an organizer. Adit is also an organizer. Shreya is also an organizer. And we are all good friends with each other.
Yeah.
Okay, guys.
And like all good graph theory problems, friendship is mutual.
Yes. Yeah. We assume we are not directed people. So yeah. This today's session will be about inversion and like projective geometry introduction. So we will like first cover few theory points and like if some of you know or like you understand something and you don't have anything to do, you can just try out these three problems for like time pass. They are like really easy problems as you can see. So yeah, take a screenshot or what. So what is this annotation? Like stop annotation. Stop like yeah. Yes. Okay. So we will start with inversion. So first of all, what is the inversion? Okay. So inversion is like one kind of like map, like transformation. So what like general kind of transformation you have seen is like suppose you consider line and you have point. So you have like reflection, which is also transformation. You also have other kind of transformation like rotating. Then your transformation of some segment by like homotopy. So now we will talk about inversion. So inversion is transformation about circle. So for doing inversion, we need first of all one circle. Suppose this is a circle omega with center O. Then suppose consider any point P, like anywhere we consider inside a circle now. Then we do a like transform P to like some P dash with definition that what OP into OP dash equal to R square, and R is the like radius of omega. Okay. Yes. So like basic transformation is like you consider any point and then you send it to P dash such that this equation should satisfy. The Now we will like see why this is so useful, but let's observe few like basic things. So like if any point inside a circle, then you will just send it outside because like this is less than R, and because this like what you call geometric mean is just R, so it should be like greater than R other part. Suppose you consider any point on the circle, like suppose this point X, then OX is already R. So like OX dash will be also R. Also, yeah, with this, there is one more property that P dash should be collinear. So like when P sent to P dash, the center P dash should be collinear. And that's why X will send to X itself. So circle remain to circle itself,
And
the original.
in particular, P prime should be on ray OP, not the other way.
Yeah, yes, yeah, that's also fact. Yeah, because we take like directed length, so R square. So it should be on this side. So the one of the like the key way to like visualize what is happening, you consider like suppose you consider circle with like large radius. So consider larger radius. So if you consider so large radius that it just become line, then if you just calculate the thing, it's just reflection. Like if you consider any point here, wait, sorry, yeah, it just become reflection type of things. I guess at larger radius, the any point the center will go here, and so the point will be just reflect. That's like key part of the inversion. So reflection can be also considered as inversion with infinite radius. But yeah, we will not go at that right now. We will start doing some basic observation. So first of all, we have some circle, center, omega. So now consider some 2 points, suppose P and Q. And now we invert them. So Q will go to Q dash and P will go to P dash. So what can you say about this? Like, so what we have? OP into OP dash equal to R square, and this is also equal to OQ into OQ dash. So what can you say? Uh, yeah, they are cyclic. So because of like power of point, we can say P dash. Why this? Okay, Q dash Q are cyclic. Yes. So these lie on circle. So this angle is equal to this angle. So notice like if you ever sending to PQ or like any segment to like inverting, we are automatically getting another cyclic quadrant. And now you can also notice the angle. So this angle just become equal to this angle. So in that sense, now we can actually change the angle up to like inversion. So let's just like try to change like some angle if you like. Suppose you have some 3 points. Okay. Right now we will consider these two collinear. And suppose you invert these points. So A, B, C, O. So A will go to here and B dash will go to here because B dash is like farther from O. So inverted B like B dash B is farther from O. So B dash will be closer. And there is a C dash. So can you okay, wow. Yes. So suppose this angle is C. Can you say anything about this angle? Also, like because I mean, what an image it will be bit of yeah. So what we can say is like okay, first of all, notice this angle B, or more like okay, this angle B will be equal to this angle because uh, B C B dash C dash cyclic. Okay, then this angle because C A C dash A dash also cyclic. This angle A will also equal to this angle A. And as a B minus A is C, because of external angle, this is also equal to C. So like if you inverted with like 2 points on one same segment and C, the like internal angle remains same. And this is sometimes like so much useful because like after you invert, it's bit of hard to angle change. But like you have to use to it. Now we will cover another nice part of inversion. Okay, yeah. So we will start with why we using inversion basically. So if you consider any line, okay, this is center O. So where will this line go to? So like you consider each point on this line and you try to understand where all the points go to. Because like as we are doing this transformation, we try to find nice properties. So how can you like first try to go for it? Like how can you find this inversion image of this line? If you take some any point this R, then this point will go to R dash. So you consider some any point Q, this point will go to Q dash somewhere. So like anyone have any idea to like first like do something? Yeah. Okay, there's a chat. Okay, there's some. Yeah. Okay, so first of all, we go for this. So because we have line and the O point is important, it's obvious to like consider like feet from O to this line. Suppose this feet is P. So like the only thing we can play with O and the line is like PP. Then now where P will go to somewhere P dash. Okay. But now consider any point R on line. Then the image of R dash, we get like P, R, R dash, P dash cyclic because of the power of point. Okay. And then because this is 90 and this because of power of point, so this is cyclic coordinator, so this will also be 90. So we basically get like R dash lie on circle with diameter OP dash. And now you can like you can move R dash to anywhere, like up here, down here. You will get all of these points actually lie on circle passing through O. with OP dash diameter.
Okay, I have a small issue with this.
Yes, yeah.
And my issue is that can you really get the point O explicitly on this line? Because, well, for that, the point would have to be infinitely far away, which does not make sense in our current understanding of geometry.
Yeah, so first, like basically, if you consider like we transforming any point to like some point, right? So if you consider point so close to O, that will like technically go so far away. So basically infinite. So
Okay,
we,
but doesn't that mean that we can go as close to O as we want, but we can never actually reach O?
yeah,
Okay.
yeah, because like sometimes we define the like things without like considering the limit case. So like we do not invert the O. But in like while solving, like I have never seen much application, but like you can just understand like roughly understand that O will go to some infinite point. Like there will be not some point this which will invert to O. O don't have image basically.
Okay.
Yeah. And except O, all of the points have image. Yes. Now, yeah. So first of all, so notice this like line go to circle. The like it's not that interesting. But now we will reverse the thing. So yeah, one of the like now we will like also use one of the nice property of inversion. So suppose you consider this circle O omega. Now consider any random circle. Okay, let me consider nice. Yeah, random circle. This is also omega. Oh, this is I don't know. Okay. This is another circle, and now we invert this circle. Where will this circle go? Anyone have guesses? Except the people who already know. Radical axis. Okay. So first of all, like let us look at like some things. So like suppose you consider this point P on the other circle, where this P will go somewhere here, like P dash. Okay. So this point will also go to some other point. This point will go to somewhere here, like this Q will go to Q dash. So, but there are we have some special point right now, like not always, but right now we have. So this intersection, where this yeah. Yeah, so A and B will go to like A
Wait,
will
they are
go
doing classes in Zoom? What the
so
hell?
yeah.
Zoom, yeah.
Okay. So A will go to A and B will go to B basically. So like these 2 points get fixed, and now you basically consider like suppose you consider this antipode. So like the center is Oda, like suppose center is N and some point R here. Then any point on this circle will make 90-degree angle with this. And if you invert the R, you get R dash. And if you invert as P is P dash, then again P R dash P are cyclic. And that way this is 90. So all of the like P dash is like locus of point such that angle O R dash P is 90. Okay, yeah. So now what? So if you consider any point on this line, so that point will go to the some this line. If you see the line perpendicular to OR at R dash. So basically, what we conclude is like this circle will go to some line. So can you see like we circle is like totally different from line as far as we work with. But now you can convert the circle into line. That's the beauty of like inversion. So like if you have like anything work with a circle and you are like make like it's feel like so complicated, then you can just invert and make it a line. Okay, why it's useful? Yeah, we will go for it. But yeah, there is another one thing. What? Okay. So if you consider like there are more few properties. So like suppose you consider some circle here, then that circle will basically go to like another circle. This will go to here. This will go to here. Like this. Yeah. This can you can prove this thing because like power of point with these 4 points and these 4 points give us like circle will go to circle. Now circle passing through O center will go to line. Line not passing through center will go to circle. And consider suppose some line. Oh wow. Okay. Some line passing through center. O. Where will this go? So like suppose any P will go to P dash, and some point Q will go to Q dash. So like the line will go to line itself. If line is passing through O. Yes. Now for like to see why this is so useful, we will try uh one nice problem. Okay, there is another thing, bit of technical but sometimes useful. Suppose you consider center O and like consider this. So this is B dash, this is A dash, this is A, and this is B. By the way, if anyone have any doubt, I'm going too fast or like you did not understand anything, you did not like heard anything properly, just ask because yeah, if I'm going to first tell me also. Okay, so we invert A to A dash, invert B to B dash about this omega and center. Now we have A dash B dash AB cyclic. Now if you given AB, then you can actually find the A dash B dash length. Can you guys try to prove it?
Sorry, what do you have to prove?
What is like length A dash and B dash?
Oh, okay.
Yes.
In terms of
In terms of okay, like OA, OB, and AB, because they are like given points. Like AB are given, O is also given. Sir,
And radius, right? Because radius would matter.
radius because yeah, we have circles, so we have to consider it. Yes. Just 2 minutes. Okay, so what we have? We have this cyclic coordinator, so we can maybe try to chase something.
a similar triangle.
Yeah,
OAB
similar.
similar to OB dash A dash.
Yes, because this angle is B and this angle is A. This angle will go to here, this angle will go to here. So we have OBC, triangle OBC, similar to triangle O other side, B dash, A dash. So now we can actually use like similarity to conclude that, okay, A dash is this angle. So we get B dash, A dash, which concludes us to A dash, B dash equal to, okay, you can write OB dash as a, I guess, R square by OB. So
Triangle
this,
OPA dash is similar to triangle OAB dash.
wait, yes, that's also like that. So like if you see this is cyclic coordinator, so this angle will also equal to this angle. But yeah, we can just like prove in this way also. So like consider, so this is will be R square into OB into OA into AB. So if you see, this is like quite a nice formula for like A dash B dash in terms of this thing. And
Okay.
now,
We
yes.
have a doubt by Shreyan in the chat. What
Okay.
happens when you compose two inversions? Since inversions are functions, what happens if you compose two of them about two different points?
Okay, so there is one fact. Okay, first of all, if you invert something like if you invert P to P dash, and now you again invert P dash, then you will go to P. So if inversion is function like transformation, so it is function. The function is involve like what you call it.
Involution.
Involution, yeah. So like if you apply it twice, it will give the same thing. That's the one fact about. And what, yeah. So there's like, yeah. So if you do inversion about like another random point, the inversion, like in the inversion is like inversion. Basically, like if you invert about O and P will go to P dash. And if you basically first you invert about O dash, then the same thing will be followed. So
I don't get. Is inversion plus inversion rotation? Is it inversion plus inversion? Inversion, what is it?
So basically, inversion, like what you call stay, like what you have
It does nothing. If I do
preserves.
two,
Yeah, inversion preserves inversion basically. Like if you're doing inversion in this diagram, and now you first you do this inversion, some other point random inversion, the same inversion will work even the inverted diagram,
so
and
it
that will
will.
give like same kind of points.
Yeah, so I guess that tells us key inversions commute with each other.
So basically, inversion plus inversion equals to inversion.
Yeah, kind of like not equal to, but like it's preserve the inversion. It's like
Like
first inversion
inversion
does.
1 of inversion 2 of something is inversion 2 of inversion 1 of something.
Oh,
But
so
Yeah,
inversion composition can do some very random things in
yeah,
general.
they can do very random.
it's random. It's not going to be neat
Yeah,
stuff.
It's not easy to classify.
It's not
yes,
another inversion.
not really. Yeah, no, it's not another inversion. You can say. Okay, we will start with one problem. Let me search for one problem. Should we start with easy one? Okay, let's start with this problem. And yeah, I'm
Wait,
thinking
just
about.
like a small comment for Shreyan's thing. Like if you have two circles and if you're composing the inversion, like an easy example is if you consider a line, it if you go to the first circle, it will go to a circle centered at the center of that circle. And now if you invert that circle again, that will go to some circle not centered at the center of the other circle. But on the other
Ah,
hand, if you directly invert the first one, it will go to a circle. Okay, this I should probably write this down, but we'll take this up later.
okay. Nah, the one like the what I guess they saying or like something different. So if you consider some circle, another circle O, and like suppose this is tau circle with center N, and if it's good like okay, get inverted to this, so center will not map to center. That's like one of the important fact. So like center will map to somewhere here, some near to the center, because like the midpoints are like not that really good
Because
condition.
you're taking like the geometric mean, not the arithmetic mean.
Yeah, yes, geometric mean not that. Yeah, that can also. But like you can see if like you draw common tangent, then like because these angles got preserved, they are like common tangent only, and so. But okay, so we will first start with very nice problem. Okay. I hope everyone understand till now what is inversion and how transformation works and so on. If anyone have doubt. And also like anyone solve the like the buffer problems I gave, DM. How much time is it? Okay, half an hour. Okay. Yes. So okay. So like let's just first let me like describe the problem. What are we have? We like I haven't even like remember the solution. So we have to figure it out together. So this tau 1 and tau 3 is externally tangent and at same point. So, okay, this will be tau 2. Oh no, what is this step? Wait, this is tau 2, tau 4.
Also,
I'm
small
not.
question, is that symbol tau or gamma?
Okay, guys, it's gamma. Okay, that no, I don't know Greek, guys. I just learn English. You might like it's gamma, whatever. Uh, suppose that these two circles intersect at A, B, C, D. Very precise. And now we have to prove, yeah, all of these points are different than P, and we have to prove this random side condition. So one of the ways to do it, like so many people will like excited for trig bash or some length chess. We are not doing that. We are doing smart work, basically. So as someone mentioned, but I will like to point out. So like if you don't know the inversion, this problem seems so hard because like you have some random four circles, you have to do some random four. Yeah, trig based people. I don't care. Okay. So like we have some random four lengths. So how you will work on it?
Similar
So
triangle.
yeah, but
Hmm.
similar triangles, but how you like find AB? A and B lie on different circles, right?
So they also lie in one same circle now. So we can say something about
Yes.
that angle equals to this angle, right?
Hmm.
So I
But
think we
like
can
not
do.
really like how you communicate with these angles with these triangle angles, right?
Oh,
Yeah. But so like the fact like obviously come up with when you like learn inversion is like yeah, you do inversions. So like now like what inversion giving us? As I told, the circle passing through center of the inverting circle transform into line. So what is like obvious point to invert it? So we should invert it like P. So now consider any random circle. Okay, wait, let me change color. So consider any random circle center at P. This is omega, and now you invert at omega. So invert at omega. Now notice what we will happen. So the this okay, I don't know, it's gamma, I guess. So gamma 1 passing through P, right? So it will transform into line. Gamma 3 passing through P, it will also transform into line. Now there is one key fact if you notice. If two circles are intersecting, the inverted image, the intersection point also go with some point, and that point has to lie on both of the inverted things. So like there is only P is the intersection point and there's no other intersection point. So basically this line like L1 and L3 should not intersect with each other. Or like if you go in projective sense, it should intersect at infinity because P will map to some infinite like large point. So this is like because tau 1, like not gamma 1 and gamma 3 are externally tangent, we get L1 is parallel to L3, right? Yes. And similarly, we get like as a gamma 2 and gamma 4 are like external tangent. L2 is parallel to L4. So okay. And also notice what is the A? A is the intersection of this gamma 1 and gamma 2. So it will be also intersection of L1 and some L2 point. So now we will work in inversion diagram. So suppose consider this inverted diagram. And after inversion, what we will have? We will have some L1, L2. So consider this point P. This is L1, this is L3. This will
Sorry,
be L2.
just confirm it. These lines will be the radical axis of the circles, right?
No, this will be some external line, right? And this will be other line. They will parallel to radical axis. Yeah, if you think it parallel. Yes. Okay, now what is the intersection of L1 and L2? A dash. And this will be B dash, this will be C dash, this will be D dash. As so many people mentioned, yeah, this will be the parallelogram because this is parallel to this.
Wait, sorry. Um,
Hmm.
the lines will be the line will be the radical axis of the red circle and the circle, right?
Oh, okay, red circle.
Yeah.
Oh,
Yeah,
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 yeah.
yeah, yeah.
The omega and the gamma.
Okay.
Yeah.
Oh, okay, okay. I thought the radical axis of these two circles. Yeah, 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 sorry. Yeah, they will be radical axis basically. But yeah, we don't have to actually like work in this diagram. This will you can even consider like large enough circle of any radius, right? But yeah, now what we have to deal with? We have to deal with this length conditions. But now you can actually like notice like because this is parallelogram, we get a dash b dash equal to c dash d dash, and like b dash c dash equal to a dash d dash. And now by using these things and also like b dash d dash equal to a dash c dash, you can actually get this. So let's just do this. should we do this length thing? Okay, what we have to A, B, B, C. So the R square will cancel out commonly, but yeah, now we will consider PA into PB will be A dash B dash, which is also equal to C dash D dash, which is also equal to CD into R square into PC into PD. So this will like give us AB by PA into PB equal to CD into PC into PD. And similarly from other side you get, I guess, BC equal to PB into PC equal to what? AD. AD equal to PA into PD. Then yeah, then I guess we just multiply the both equation and you get and divide, do this in other side. This will be equal to what? Multiplication sending here. Yeah, PA into PC by PB square equal to PA into PC by PD square, which gives us PB square by PD square. Yeah, that is indeed what we want. So like this seemingly random lengths just become like parallelogram. So that's like usefulness of inversion. Once you like invert about the circle, like point on circle, it actually becomes so easy to handle. So everyone understand like how useful inversion is. Now we will try another.
Siddharth asked if you can explain why it's parallel again.
Okay, yeah. So because this gamma 1 and gamma 3 are externally tangent to each other, if gamma 1 map to L1 and gamma 2 map to L3, the L1 will be parallel to L3. Because if it has another intersection, the circle should have another intersection, but circle only have P, which maps to infinity. Yeah. So L1 will parallel to L3, L2 will be parallel to L4. The inversion of gamma 2 and gamma 4. Yes. And so this you can see like L1, L3 is parallel and L4, L2 are parallel. And so the intersection, this will be parallel. Yes, nice. Two circling. Yes. Now we will go for what can I see? You guys want another problem to work on? Let's just see another so much.
We discuss the buffer
useful.
problem.
What? No, like okay. First, we will take another nice.
The buffer problems are meant to be buffers, so I don't think it's
Yeah.
intuitive to
We will
discuss.
cover another nice problems. First, now we will cover like one of the most useful like fact about inversion. Like basically, you can use it in every triangle geometry problem. So let's do root BC. Yes. So what is the root BC inversion? So consider any triangle. Finally, we back to circle to triangle. Now this is weird, like we working with triangles, but like inversion is only work with circles. But that's not fact. Inversion actually is so much useful. So, wow, there's like some random photos going on. Okay. Yeah, inversion sometimes give neat solution. We will now talk about it. So, what is root BC inversion? So you invert at A, okay, with radius equal to root AB into AC. ABS is like DC in like a commonly known term. So we call it root BC inversion. And plus we reflect about angle bisector. What is this? Of angle A. So consider this angle.
Center of the circle supposed to be A.
Yes, center is A. I did not mention. So you consider circle center at A with radius this. Then you do inversion plus you do reflection about angle bisector. Now, first you see this is like randomish thing, but now let's try to see what we are actually telling us. So where does B will go to? B will go to some B dash, like at first, like first transformation, B will go to B dash, such that what AB dash is equal to what? AB into AC by AB. So this is just AC. And now after like second transformation, this reflection, the B dash will go to another point, B dash. So B dash will go to B dash. Yeah, this is called B double dash basically. And B double dash will lie on AC. Because if you see the reflection about angle bisector of AB, go to AC. Because we just literally consider angle bisector of line AC and AB. So this AB will go to AC. So this some point B dash here will actually go to here somewhere on B dash, such that B dash is equal to AB dash, okay, AB dash double dash, yeah, equal to AC. So that's just supposed to mean B double dash is equivalent to C. So basically, when you do this inversion plus reflection, B will go to C, and if you follow the same thing, like C will go to some C dash such that AC dash is okay, AC dash is equal to AB, and the reflection gives C dash to A. So the key fact is like B will go to C and C will go to A. Tada. Another thing. So notice like there is circle passing through A, right? So ABC, circle ABC pass through A. So it will map to some line. It will map to line of inverted image of B and C. What is the inverted image of B and C? CB, right? So this circle will map to CB. So actually circumcircle of ABC will map to BC, and B will map to C, C will map to A. And the BC will map to circumcircle of A. So like this is like beautiful thing, right? If you like have a like suppose you have some point P here, then that will like the inversion will map to some on BC, some point on BC, just BC. And if you have some like yeah some point Q on BC, then that will map to Q dash, and that follows like the angle condition and thing, which we will now talk about. But yeah, so like the key point is these two things. Now there's another thing. So where will the angle bisector will map? So if you have some angle bisector point, that will like if this point inverted to here, then that will map to itself because angle bisector never change by reflection. So there's another thing like if you consider in center I, okay, where does in center will map to? It should map to some circle on like angle bisector, right? And now you can actually use like other thing like you if you know this in-center lemma that if external angle bisector is J, then I, B, J, C cyclic. So now you actually when you invert, I will map to some I dash, J will map to some J dash, and B will map to C, C will map to B.
The J kind of like the X center. Okay.
Yeah, X-center, okay.
Oh.
Oh, I did I say something? Okay, anyway, fine. Okay, actually, rather than this, there's another neat way to do it. Okay.
This is like in center, X center lemma, right?
Yeah, in center, X center.
Also, a small thing for those of you who did the problem in the P set, there was a problem involving 4 circles with their in circles and their in centers being concyclic if and only if their X centers were. This was the key lemma, the fact that basically I maps to J under root based inversion.
Yeah, so like you can do like angle change here. Basically, I think like if this maps to here, then this angle should equal to this angle, which is true because this is like 90 plus C by half, and no C by half, and this is also 90 plus C by half. So I will basically map to J. And so this was like key lemma in the problem also. And this is actually very, very, very useful that IA, basically this part, IA into IJ is equal to root ABC. or which is in our term like AB into AC. So wait, not
Root
root.
IA times root and
Yeah,
root AI times root AJ. So yeah.
yeah. So this is like very useful in some other way if you like try to work on. So like if you consider it like external what X circle of B and C also, this thing also like inverted to each other. And this gives us like very nice factors like I is a ortho center and so many more things. We will I guess cover that also. We get time. Okay, now what we can cover? We can now try one nice problem on root BC inversion. So basically, remember root BC inversion do like convert like we do inversion and then we use reflection. Let's try this problem. Quickly hide some. Okay. Then we will do some other nice inversion. I will give like 2 minutes to work.
Since these
Yeah.
problems have like numbers and stuff, I'm assuming they're from a book. Which book are they from?
Yeah, the what Euclid EGM.
Okay.
Yeah. Yeah, I will covering some other things too.
What was definition of median again?
Oh yeah,
Median. Okay, the definition of median is that it's the reflection of the median about the angle bisector.
yes. So you like if you have some triangle and you have median, consider like angle bisector. Then if you reflect the median, then we get this median. Now median have so many nice properties like it's passed through. If you like consider external like tangent to BC and CA, the median pass to this point T, and then median have so many nice things like Dumpty point and so. And that was like in our P set.
How did you
Like,
prove that again?
no, we will like prove. Let's just do this problem. That is also like you can do by inversion.
The proof is an
Inver-
exercise to the viewer.
yeah, proof is exercise to do, and it can be done by inversion too. So it will be fun actually. Okay, let's just see the problem. So we have ABC and how much time it went. Okay, I need to be quick. We have BC. Then we have angle bisector intersect BC at D and omega at E. So first of all, can you guys notice something? Like we have angle bisector and like triangle and circle.
D goes to E and E goes to D.
Yes. Also, like if some point D go to E, then like because of this thing inversion, you can like automatically say E go to D. And similarly, this is very useful. Like sometimes circle go to line, then you can consider any point on that circle, and that will go to that line only. We will see that also. Okay, so then what we have? Circle with diameter meet at F. So this is circle with diameter, this meet at F. I should zoom. Okay, and then we have to prove AF is median. So, like by definition, what do we want to prove actually? AF is median. That's supposed to mean
Reflection
AF
of
is
AF about AD is the
yes,
median.
yes.
Yeah, and
So
F.
that automatically like inspires us to consider midpoint of BC. So if you consider midpoint of BC as M, so like let
Oh, then
what?
M also lies on the circle.
Yes,
Yeah.
let M be midpoint of BC. Then what is this diameter telling us? Diameter supposed to mean this angle is 90. But can you notice something? Because of
Yeah,
in
is
center,
midpoint of arc. So
yeah, in center lemma, E is a midpoint of arc BC and M is midpoint of BC. So that will just give us this angle. Angle DM is 90, which tell us M lie on this circle with diameter D.
That
So
also
I'm
tells us that F will go to M right after inversion.
yes, yeah, we will see that. So yeah, you are right, Atharo. Yes. So what will happen? So now you will do root BC inversion. Basically, we are doing it root BC inversion. Yeah. technically we do root BC inversion. So BC will maps to ABC. Okay. So now where does D maps to? So D map to E, E map to D. So circle with diameter D will map to some circle with like D only. Now because the diameter, the center actually lie on D itself. And because we already prove like something like if this map to some point another, like suppose the map to this will again 90. We proved before, right? So that will automatically give the circle with diameter D will map to circle with diameter D itself.
Yeah, or you can just say ki by power of point on A, the length is always
Yeah. Yeah,
divided.
Or we can just say that D is the closest point to A from the circle and E is the farthest point.
Yeah,
So
yeah. But
closest
like,
point maps to farthest and farthest point maps to closest.
yeah, you
I
can
didn't
say
get
that.
your argument. I didn't get your proof. The closest farthest thing.
So
No, so thing is like you considering some circle and like you mapping like this is D is a diameter, right? Now you map this circle to somewhere else. So D go to E, E go to D. Then like the farthest point go to closest point go to farthest point. So this circle actually preserves itself. And now if you guys like look at the observation, some circle get preserved under inversion. We will come to that also. That's actually one other nice fact. But okay, let's do this problem. So we prove M lie on D. So if like M dash is image of like M dash is image of M under inversion, then M dash should lie on D itself, right? Also, as a M lie on BC, M dash should lie on ABC. But what is the like common between these two circles? F. So because of this like bijection kind of thing, we get M dash is actually F itself. So F will go to M in inversion. And as a like the definition of root BC inversion is reflection about angle bisector. The AM is reflection of like AF is reflection of AM. So AF is median. Tada. Do you guys like get? So like if you like this is triangle problem. There's nothing more circle. There's just one circle which is like obvious circle ABCD. But still no ABC. But still you use inversion. And this is like beauty of inversion and like fact about root BC inversion that you don't need so many circles. But later on you will know like there are more circle passing through A and which become used like then root BC inversion become like so much useful. But yeah, here the main fact was like D map to E because they are on angle bisector. Then M also lie on the this circle, and that's why M will map to F because of bijection. Like M lie on BC, M lie on this circle. So F is like the same as a image of M. So everyone understand the thing, right? Okay.
Yeah.
Now we will do another few Okay. I guess it's time to do some harmonic things, but I will like left you guys with some nice problem. Just give me 1 second. Yeah, this is one of my favorite problem of root BC inversion. If we like cover the harmonic thing quickly, then we will do this or other. Yeah, try this at homework. Another backward problem. Okay, let's go for harmonic. So what is harmonic? So what happened? So geometricians just sit down and they try to think about the life, basically segment. So they consider like they want to find some common property between some like transformation basically. So basically, first I will tell the definition, then I will like tell how they come up with it, which is actually very nice. So consider some point A, B, X, Y on line segment. So we define this as a cross ratio. My pen tablet sometimes do some weird things. As a what? I guess xn to xb divided by yn to yb. Okay, many books have different definition, but like the thing is same. They can just change the they first take A or B or something. But yeah, these lanes are directed by the way. So like XA is XA only, it's not AX. XA, XB, YA, YB. And this is how you define cross ratio. This is called cross ratio.
Now the natural question is, why would you derive something which looks so weird?
Yes, that's a good question. But now we will like go for it. So first of all, this is cross ratio of like, yeah, we consider cross ratio for 4 points. Okay, four. Remember the four. Uh, then now we will let there's cross ratio defined for 4 lines. So if you consider some 4 lines passing through this point, yes. Now we like some we many times we just call line by small letters. So we call this line A, line B, line X, line Y. Then we also define cross ratio for A, B, X, Y. Yeah, so cross ratio for the lines which have common point. So if we have some common point P and there are 4 lines passing through it, this cross ratio is sine, how do you define? Okay, sine angle XA. So like angle between X and A by sine angle between X and B, and then you do the same division thing. What is this? Y. Yes, YA and sine YB. This is like definition still, okay? So this is cross ratio for line. Cross ratio for lines. Concurrent lines from P.
Is there a geometric definition?
Yeah, this is kind of geometric. Now we will see why this is so useful. Now, suppose you consider some 4 lines, okay? Because we actually work with this line so much. So this is P, this is A, B, X, Y. We define the cross ratio. Now, suppose you consider another line L, and suppose small a intersect L at A, B, and X, Y, similar, like respectively definitions. Then what is the obvious thing come to your mind? First you see this. We define cross ratio for lines. We define cross ratio for 4 points on segment. So maybe the cross ratio for lines can be equal to cross ratio for points on segment. And in fact, this is true. Yes. See, why this is true? Actual, like you can use ratio lemma. Like you can just chase this angle with this angle, this angle, this angle, and this angle.
Sorry, what's ratio lemma?
Okay, ratio lemma is this thing. I mean, this angle change is bit of like sine rule stuff. But yeah, I will just tell you what is ratio lemma.
Aren't you just using that sine theta is equal to
So,
this?
okay, yeah. So AD by DB is equal to what? PA by PB into sine. I guess sine in yeah, this angle APD. Okay, I am not taking that directly because I followed directly, but it should be this one. Yeah. This is like ratio lemma. This is even like just proved by like sine rule,
Oh,
not cosine rule, by sine rule. And yeah, so you just use this angle, and this is 180 minus that angle. And so you get this ratio lemma. And now you repeatedly apply this ratio lemma at some 3 triangles, and you get this equation. We will omit the proof here because that's not like point of the thing, and it's like bit of lengthy things to do. But yeah, just believe me, except here, we never use trigonometry like projective. This is such a bad part that we have to use like trigonometry at the core definition, but you never have to use it again. So now you finally have cross ratio. So what can you say more about this cross ratio? So this cross ratio is equal to this. So if you consider another any line L dash, and if you consider other intersection, okay, X dash, B dash, Y dash, then this cross ratio will also equal to X dash, B dash, A dash, X, B dash, X dash, Y dash, basically.
So basically for all lines.
Yeah, for all lines intersecting these 4 lines. So like cross ratio getting preserved. If you, and what we call it like projecting from L to L dash. So like if you project the cross ratio, this cross ratio ABXY from L to L dash, it will be same for the intersection points. You guys understand? Now, like we can now move on, but I will just for like sake of so many curious mind, I will just tell why we actually define the cross ratio. So what happened if you look at like, okay, I will give simple example. If you look at a conic, you have this circle, right? And now you consider any plane. So if you this intersect at ellipse, right? And suppose you consider some plane like this, then it will intersect at hyperbola or something like that. So we like, because of this type of thing, this is actually called like projective transformation. So this circle is on some plane, this plane P1. This thing is on P2, which is inclined to P1 at some angle. Then this circle actually project to ellipse or something, yeah. And so what is actually happening? We projecting one plane to another plane. A mathematician actually do so many things with this. Like you can project to like this with same angle as infinity. So like you actually get like infinitely far points in P1 to like so many like just line at P2 and so many things. But this is called like projective transformation. Like you transform plane to plane. And now the key fact in projective transformation is the cross ratio. So cross ratio on any like four collinear point, what it will map to, it will map to some line. Okay, let me give. So this is like some plane 1, this is plane 2, and there is like line which also map to some line. Then this, if you see the cross ratio on these four things, will also equal the cross ratio on this pencil of lines. Okay, so line passing through same point is called like pencil, just like definition. So this pencil of line has same cross ratio as this, and which also map to this in same cross ratio. So basically projective transformer preserve the cross ratio. And it's like some with some more one condition, any transformation with sending like plane to plane and preserving cross ratio is projective transformation. So there is like so many deep theory, but this cross ratio is like innovative and which is so useful. That's why we consider the cross ratio. And that's why mathematicians come up with such a weird expression, but very useful. Okay, now what we will cover. Okay, we suppose any conic. So we drawing like ellipses, but you can consider any conic like hyperbola and parabola.
Question,
We
what
also,
is a conic defined as?
conic is like 2D, I guess, shape in 2D per. I mean, like just define it conic, right?
Okay.
Okay,
It's a
basically,
shape with cutting a cone in different ways.
yeah, that is another definition, that if you consider a cone, you intersect with plane and then you will get some conic configuration. Or another is like any equation with like in like x and y with some like same coefficient or something like that. Okay, I will come back to it. But yeah, first of all, like any conic for now, like you can actually prove any conic is just ellipse, hyperbola, parabola. So consider any conic. So it is A, B, C. I forgot the definition. Okay, then you can actually define cross ratio for conic itself. So this is conic, suppose what? Name some random. This is called omega, right? Yeah. So this is conic on like omega, conic omega. And now the cross ratio for ABC. There is a cross ratio for ABC, which is like same as like cross ratio of these lines. AP. Yeah. So we define cross ratio on conic omega as this cross ratio of pencil of line from P. So you can actually define cross ratio for conic. Then you can go conic to conic. Basically, you can transform a project from conic to another conic if this point P also. Then yeah, this is so cool
How
fact
do
because
you
so no, okay, I will tell what I'm saying. So consider some this. You can actually like, suppose this is the conic. So what actually we have from this conic? This is ABC, right? And suppose this line intersect at A dash, B dash, C dash, D dash. Then you can transform the cross ratio ABCD into like this will equal to A dash B dash C dash D dash basically from P. This can be true because see the cross ratio defined. This is any conic. Conic can be circle. In our day-to-day life, and day-to-day life means like Olympiad many times it just becomes circle and you just use circle. But yeah, this any conic just have this definition cross ratio. Now you can just project from P to some line L with this intersection and this cross ratio are same. The only condition you have to remember that P should lie on conic because like we defining this point like cross ratio for like conic itself. So this pen syrup line will have some same cross ratio and that's why you can just transform the cross ratio. Now there is one another interesting fact. Okay, weird. And there are like another the way I was like stop talking about what is conic. The another way to define conic is like if you consider some point K such that the cross ratio so K, KB, KC and KD are constant, some like some M, then this K will lie on some conic passing through ABC. This is actually like cool facts about conic and so. But we will now like skip about conic. Like conic generally, if you want to study about conic, you can like refer to some handouts and so on. This is like much more like into projective transformation and homography things. But
How
I
do
hope
we
everyone.
prove it? How do we prove that cross ratio is preserved for conics? Circles are easy, but ellipses?
Okay, what do you mean by preserve? So this is cross ratio on conic, right? ABCD. Now
Yeah.
this cross ratio is equivalent to ABCD also, right? If you call these lines ABCD, small a, small b, small c, right? Now
Okay.
this cross ratio is equal to this, like when you project the cross ratio of pencils to line, this will be preserved. And that's why cross ratio get preserved. And that's why there is important condition that P should lie on that cone. Because you cannot say this pencil of line equation is same.
But how do you prove the first result?
What? Okay, this is the definition of cross ratio on conic, right? The way you define like cross ratio on conic is like this pen syrup line cross ratio. So like the ABCD cross ratio on conic omega is actually equal to this PA, PB, PC, PD lines.
Does it depend on the position of P?
Yes, that depend. Yeah, that depends. But like the fact, like the special fact about conic is that if you take any point on conic, that this thing actually preserved.
Right,
Like
same.
that's same thing, and that's like that is you can do by like projective transformation. Like you transform this conic to circle, and that just remains that.
What
Okay,
if we
so
take
there's special.
P to lie on one of the points?
What P? Okay, that's because you cannot do this thing if P is not lie on conic, right?
No, like P lies on one of the 4 points.
I wait, limited case, right? I guess that works, but that requires some kind of casework, like how you
Would it
define.
become like a tangent to the conic?
Yeah, tangent. Yeah, we can do that actually. Yes, you can take P as any point. Yeah, and there's special fact of a circle. If you consider any 4 point on circle, and now you try to define the cross ratio, right? The cross ratio will be same as a conic, uh, which will be like PA, PB, PC, and PD. There's another way to write this thing like PABC. Just like assume that P is written outside, that's supposed to mean we consider pen syrup line from P to these 4 points, the lines. And now this cross ratio is actually equal, like because like these things you can do like what you call sine rule. You can repeatedly apply the sine rule to prove this is actually like length thing. And I don't remember, but like some length condition with these 4 lengths. Okay, I will come back to that. I don't remember the exact length.
I guess
Can
you can
you?
use it's right diagonal, right?
Yeah. Okay, but anyway, now we will come to like one of the main point of like this thing. So the cross ratio, the cross ratio AB is XY can be negative too. So if this cross ratio become -1, then everyone just like cheer up because like they have this cross ratio as -1, which we call harmonic.
The reason we call it harmonic, I think, is because then AX, AB, and AY form like an HP, if I remember correctly.
They form HP.
Um,
Uh,
how will it form an HP? Doesn't HP involve
that's not fine. Like, okay, we
one
call it
by
harmonic
something?
because we like the name harmonic for now. Uh, but now what is like main use of harmonic is
Yeah.
like so many uses of harmonic. So
There's
we
nothing
start
special
with
for one.
what?
Is there shouldn't it be one? Wouldn't it be something more special for one?
Okay, no, the -1 because of the length condition. Like we taking directed lengths, right? And this is x is inside AB and y is outside AB. So this just become like XA into XB, I guess, equal to some, if I'm not wrong, this is division, yeah. So YA into YB with minus. And this minus because of the lengths are like outside. We going this side, this side, this side, and this side. This is minus. Now, because it's directed lengths. Now, what is a cool fact about this harmonic thing is like it's give us so many things to handle. So first of all, we go for this thing. Consider any quadrilateral and some this thing, Sivas. So consider some DEF such that DEF concurrent at some point P in triangle ABC. Then you consider this point, this intersect at D dash. Then you can actually by say like Sivas and Menelaus, right? So Sivas and Menelaus actually gives like this B dash C dash is equal to some length ratio with this, but also the BD dash and CD dash also equivalent to same things. So because of this thing, like you can use Sivas and Menelaus 2 times, like 1 times, both of them. You get what you get. BC DB dash is equal to -1. So basically this condition follows.
There's another way, right? Like we can use the fact that if you move stuff from one line to another line through a point, then cross ratio is preserved.
Yeah, but
So,
like we need to define minus harmonic cross ratio somewhere, right?
Yeah, like what Adit said comes from the original one, right?
Yeah, no. So thing is like suppose this AD intersect like E up at some point R, then you can just like say because of projecting from A, this B will go to F, E will go, C will go to this, D will go to R, and this will go to D dash.
What
So this
is
is also harmonic.
A? What is A?
A is like some point, so ABC is triangle. DEF such that ADB CF concurrent at P, and D dash such that FE BC intersect at D dash.
Does this work ulta? I mean, if I have 4 points of
Yes,
harmonic,
yes. So if you so now this is like cool fact about harmonic. So if you have 4 points, suppose D, D dash, B, C, and now you consider any line from D dash intersecting AC and AB at some F and E, then because of this harmonic thing, these 3 lines concurrent at P. Yes. uh and yeah, I hope everyone understand like this is called like harmonic for like quadrilateral, and this is so useful. D dash BC is so useful because see, you can project from P. If you project from P, you get this R E F is also harmonic. If you project from A, now you can actually do same thing with respect to D dash E C, which actually give us like suppose D dash P intersect here at Q, then you actually get A Q EC harmonic. And there are like so many. Like you can say this intersection, that is also harmonic. This is also harmonic. This is also harmonic. So many harmonic things we get from
so
just
one very common theme that I can see from this diagram is that if there's a lot of lines and there's a lot of concurrencies, then projective is a good idea.
Yes, projective. So like basically you can go by fact, like if there's lot of circles intersecting at one point, you go for inversion most of the time. And if there's a lot of lines intersected at one point, you go for like cross ratio or projective things. So now we will go for another very nice fact.
One question, if you don't mind. Is
Yeah.
there any nice connection between inversion and like cross ratio stuff?
Yes, the poles polar. We'll come up to this.
Okay.
We cover some two nice facts about harmonic bundles. So suppose this AB XY are harmonic. Okay, then you can actually note down, or like there's way to prove this by inversion, that consider the midpoint of AB. So let M be the midpoint of AB. Then there are two facts. So first of all, mx into my is equal to like half of AB. No, AB half square, not half. Ignore this, yeah. Or like more likely to call MA square. And second fact is that, what is that? Don't tell me I forgot it. My into mx. Okay, if I remember correctly, it is xm into xy is equal to xa into xb. You can change x to y also. Yeah. So both of this can be done by just, okay, you define like this is on real axis. You define this is like 0, comma 0 because you can just shift. Then you define this is like 0, comma b, some 0, comma x. And you get some nice cool result because this is harmonic bundle minus 1. Oh yeah, this is harmonic bundle. So process is minus 1. And this is y. And then you define m and you do like length chasing basically, which is bad, but you have to do it at end. But if you see this carefully, what is actually telling us? Consider circle center at M with MA radius. So it's
Oh,
passing through
PowerPoint.
A and B. Yes. So because of PowerPoint, mx into my is square of radius. So x will go to y. So so if x will go to y, these things are harmonic. A, B, X, Y harmonic. And this fact is like so useful. And now you, from this fact, we go for another very interesting cool result. So consider some center O and some line, this is AB, some point X, and let's invert X to Y, right? So X get inverted to Y, and that's why we get, because of previous result, ABXY is harmonic, right? But now there is another cool thing, that is, yeah, take tangents from Y to the circle. Okay. Now, wait. Okay, this do not have to be passed through Y actually. Oh yeah, okay. Don't consider inversion. Just consider the normal points. Yes. So consider some circle omega and consider some line AB and XY such that this is harmonic. Now consider the tangent YE and YF to the omega. Then we have another nice thing that AB EY is harmonic. Can you guys see how? I will give like few minutes to guess. Yes, first condition is followed
Do you
by.
mean ABEY or ABEF?
Oh, EF, sorry. Yeah, of course, learning. We consider like cross visual circle.
Yes, because they are symmetric points.
Yes, but like no, like you cannot just say symmetric points. That's why they are like thing, right? Okay, so way to go this
They
is
don't
like,
have to be symmetric, right?
nah, they don't have to be symmetric. Symmetric, like,
Are
now
there
symmetry is like,
tangents to phi?
yeah, tangents, but like,
Okay,
what
it's random
symmetry,
line. Okay.
yeah, this is random line. So way to go this is like actually going in reverse direction is much easier. So like consider some circle and y, this is tangents. Consider some point. So y, b, x, and what was this? E and a. Now consider this intersection. And let this intersection be some point x. Now you can actually use some cool kind of trick, which is this. So consider the harmonic, like not harmonic, but cross ratio ABXY. Right now we define X as the intersection of EF with AB. And now this cross ratio, you can actually like take projection from E, which send A to A, B to B, X to F, and Y to E.
Small warning. I think there's only 10 minutes left. Like we can extend it, but 10 minutes for
Yeah,
normal
I
time.
guess yeah, we are done. Like just this cross ratio.
Then we can extend it, right?
Yeah, for 15 minutes, like 10 minutes, fine. But yeah, so this is because of like the projecting y to circle, you can just consider is a tangent, EF is tangent. And this is like projecting line to the circle. And now this is like, now you project from y. So now you project from this from F basically, so not y. This will go to like A, B will go to B, and F will go to Y, and this will go to X. If I did not miss something. Yeah. Now this is fact. So see, this is equal to this, basically. And this actually is equivalent, condition is equivalent to ABC become -1. Like you can do this Lenz's that uh yeah, so this like XA by some XY divided by YA by YB, right? And this is like just reverse of that. And they both are equivalent. And that condition is equivalent to this being harmonic. So that's why ABXY is harmonic. Now you also define the harmonic quadrature. What is harmonic quadrature? Is like if you have some point A, B, C, D. Suppose this A, B, C, D. Then this like the 4 points are like harmonic. If this is -1, so cross ratio on circle is -1. Then what nice fact about this we have that tangent at A and tangent at B. If they intersect at T, then T, B, D are collinear.
Can we take cross ratio with respect to center of circle?
No, cross ratio is respect to like conic, right? Like you define a cross ratio on circle, like
I mean, like if we just take the center of circle and and draw those rays,
okay, that is fine, but that will not preserve anything
I would not
because
preserve
we
anything.
cannot project from O to somewhere, right?
I mean, isn't it like all conics have common center on, like if you have a cone and you take the mid line axis of the cone, then all conics will have the center on the axis of the cone.
But like while you transforming from one plane to another plane, the
If the
axis need not to be like in same way.
why
Okay,
would
we
it,
will come back to this. No, okay, we will come back to this, but first let. Okay, so from this, what we have is like if you consider tangent from y, this EF pass through x, and x, y, AB are harmonic. So similarly, if ABCD is harmonic quadrature, tangent at A and C, if intersect at T, TBD is collinear. Similarly, tangent at like this B and D also collinear with like intersection, this intersection P is also collinear with AB. Everyone understand this thing. So this harmonic now just feel like some randomish thing, but this is sometimes so much useful. There's one useful application. Uh, Let me see if any of it useful application you can cover quickly. It's okay. We have 10 minutes left. Anyone have any doubt? First of all, so that we can cover that.
yes, first thing was what about the axis thing? Why won't the axis wala projection do
Okay,
anything?
this conic. Nah, that is like bit of like transformation, like project to transformation.
Yes.
Okay, anyone have doubt about class? Like what is harmonic inversion? Everyone understand the inversion and you understand the harmonic things.
Yeah.
And right now we can cover some question or we can cover one more theory about quadratic, like quadrature. Okay, basically these two lemmas, one is right angle lemma. So consider some triangle like this BC, A, and suppose like X and Y. Now, if this is 90, so first thing is like either AX, the line AX, okay, not some circle or something, is angle bisector. Of angle BAC. Second thing is like, of course, XYBC harmonic. And third thing is like angle XAY is 90. So now you have some three random facts. Okay. Now what I am claiming is if any of two of them are equal, then third is also equal. So like if A and 2 is equal, so AX is angle bisector and this is harmonic, then this is 90. If this is 90 and this is harmonic, AX is angle bisector. If AX is angle bisector and this is 90, this is harmonic. This is a cool fact. It's called like right angle and angle bisector. And this will lead us to like another cool config, one of my favorite, apollinear circle. So there's a circle with diameter S. So okay, this is bit of like kind of hard to prove. I can give it as like homework also. This is nice fact actually. And construction is like we have to construct one key point here. So I will like give
We
this
can
as
also do just like internal angular bisector, external angular.
yes. Yeah, so yeah, that is one fact. Like, okay, this is internal angle bisector. Now, if this y has to be external angle bisector, and then this is 90. But this is just like equivalent from 8 to 1 to 2, right? To do this like 2, 3 to 1 is like bit of hard. That's not okay. Oh, maths 2 is okay. And there is another very useful lemma, Prison's lemma, which is now I have to remember it. Okay. If I'm not wrong, it's A, B, C, D. Okay. The cross ratio and A, B dash, so A dash, B dash, C dash. I guess, yeah, okay, not 3 points. Yeah. So if the cross ratio between these points, like you can define cross ratio some anyhow, CA is equal to cross ratio between A, B dash, C dash, A dash, then this is equivalent to saying, I guess, wait, yeah, B dash, C dash, and A dash are concurrent. Just let me check once. Yeah, I can mess up with the definition because I forgot the limited D, distinct point, distinct.
Yeah, this seems to be all right, I think.
Isn't this
Yeah,
wrong? I mean, I can just take uh A B B dash is parallel to A dash and C dash is parallel to A dash. I can just do that
Oh,
and
right,
then
we have the
yeah,
infinity thing again. So
yeah,
those
yeah,
points at infinity exist, I guess.
yeah, points at infinity exist. Just as like the two parallel lines intersect at the secret point, which is called quantity. Yeah. So this intersect at some D.
And I
Uh,
guess this is why most length theorems like Siva and stuff are phrased as these lines are concurrent or parallel. And then parallel is just like
yeah.
concurrent at point at infinity then, right?
Yeah.
uh,
Okay, see what missed. Yeah, that's also cool.
Yeah, also,
But yeah, okay. Can you guys see how you prove this? If you consider like, okay, forgot about C, but if you consider B dash intersect at D, and now you project from DC to some point C double dash, then this cross ratio will be same as this cross ratio. So this will be equal to P, B dash, C double dash, A dash. And because this both cross ratios are same, we can say by like lengths this is equal and that C dash is equal to C double. So what is a nice fact about this? Like if you have two lines and cross ratios are same, the three lines actually concur, which is sometimes so much useful.
If you have two like
Yes. Yeah, they should concurrent at P. And you should consider the cross ratio with respect to P.
yeah.
Okay. Now I guess everyone understand like today's things. So we just randomly cover inversion. So inversion is like transformation with OA into OA dash equal to R. Then we cover the like length, the cyclicity, line go to circle with uh, like circle passing through center, then circle passing to center will map to line, which is so much useful. So like we actually change one kind of like dimension. You change circle to circle. Sorry, circle to line. What I was saying. Yes. Then we can say this cool G4, which is like if you not use inversion, it's like not nice to solve. But like this inversion like make it like so much better and nicer problem. Then we have this root VC inversion. You can actually try to find so many things. There are so many less, like I did not even tell you like 1% of root VC. So if you have some center O, you can see center O like OA maps to OH. Then if the X center of the C and B actually maps to each other. And so many more things. So that this D actually map to antipode and so on. You can actually try to learn by yourself. You can read EGMO like Euclidean geometry, Euclidean geometry in Olympiad mathematics, something like that. Chapter 8 for inversion. Second, there is like a beautiful journey through Olympiad geometry. This book have like I guess chapter 20 if I'm not wrong. This they cover very nicely every detail how inversion and things work, and they also have nice thing with root BC. And there's another kind of inversion which is like root BC by half. So you actually invert, but now you also like consider half ratio, like the 1 by half ratio. So B will actually map the midpoint of AC, and C will map to midpoint of N. Why this is useful? You can like later on know, but I will tell you like one fun fact about it, which is I like so much. The in this inversion, 9 point circle maps to circle BOC. So O is the center of circle, and 9 point circle is like circle passing through fits and midpoint. This actually maps to OC in root BC by half. This is like inversion with root BC by half plus the reflection about time. Okay, we cover this, then we cover cross ratio. We define a cross ratio for segment and pencil of line. Then you can transform one cross ratio to another. This is like, and why we define some plane projective transformation. We define cross ratio for conics. Then yeah, we do some harmonic bundle. So for harmonic bundle, we have some this cool fact like this into this like mx into my is actually ma square, and xm into my is xa into xb, which is so much useful. Like once you do practice, this is so much useful in power of point. Like each of the power of points somehow use the harmonic bundles. Like okay, expect few, but if you somehow find some harmonic things, you actually like tend to consider the midpoints of some segments, and which makes so many nice things, like which makes so if you have some like suppose some x, we have x, and you just consider some circle passing through B and A, then this, and suppose you have some harmonic conjugate of x y, then this cross the power of x with respect to this circle is equal to power of this with respect to my. So, we actually have so many radical axes and things. So if this is P and Q, then like power of X is PQ into XQ into XP is equal to XA into XB. And by this harmonic thing, this is equal to XM into XY. So that's why PQMY is cyclic and so on. So considering harmonic is so much useful. Then yeah, we have this tangent thing. That's like if you have harmonic bundle, then the tangent from y, y and yf actually like pass through X. So like this X, EXY F is collinear and with the harmonic things. And then we have harmonic quadrature and prism lamp. And this is nice fact. There are so many harmonic things you can read in like EGMO itself, I guess. EGMO chapter 9. Yes. And also there's RG's handout. I guess we shared on the server, our projective geometry, which is also nice. So everyone understand the basic. And now, yeah, I think. Okay, yes. So
Still, it would be nice if you compile some 5, 6 problems and we
oh
can
yeah,
check
yeah.
those out.
I will give. You can guys can try this one. This is like very nice inversion problem. Why it's not good. Yeah. And there's this like cross ratio problems.
That like beautiful journey.
It's from Beautiful Journey. This is like the G8, but actually this is like so nice cross ratio things. Like this is just using cross ratio. We don't have to use anything more, which make it like why cross ratio are so much useful. This is like a bit of hard problem to be honest, and this is also hard. But yeah, you can like used to it once you try.
11.2 and I was able to solve.
What?
I was able to solve the first, except for that I wasn't able any other problem.
Yeah. These are like actually a bit of like hard problems. You need like bit experience, but yeah. First one, yeah, that's nice if you're able to solve it. Because
Well,
it was
projective and cross ratio.
yeah, project and cross section. Do we want extended? Do you guys want it? I don't
I
think so.
want
Like
extended class.
okay. First of all, everyone understand inversion and harmonic cross section, right? How many students are there? I don't know.
I
Also,
understand
like,
it, but lots of
oh,
theorems I don't have proof for. Like there are lots of
Okay.
theorems in this that I have not
Like
proven.
okay,
So
I guess this cross ratio thing, like except the like why we define cross ratio and the conic thing, I guess I give everything ratio, right? The definition of like conic is like okay. I have
no,
to think.
I understood definition of coding. That was the cross ratio. What's that theorem when not proven?
Wait, what you are saying?
Cross ratio theorems which were not proven.
Okay, this thing. Oh, sorry, this thing. Angle
Uh,
bisector. Yeah, you
this
guys can try or like I can tell. So
no,
we
not
have
this.
to.
I'm saying other thing. The पहले वाला भी. For example, the thing right after uh, the can you go up a bit?
Yeah.
Up. Uh,
This harmonic or this conic
इसके ऊपर
or
I think
trans
a bit below this, like, around here only.
some theorem. I don't. This thing.
The cross ratio is conserved for ellipse wala, for example. You didn't prove that.
Okay. This thing basically.
How would you prove that?
I mean, I think a Google search should easily reveal the proof, but
No,
it will
yeah.
probably be hard to prove here because ellipses by themselves aren't very nice synthetically
Yes.
from our
No, so
perspective.
the thing is like how you actually define ellipse is like by conic, right? So you intersect plane with cone.
Huh?
And now you actually defining like the cross section 3D thing.
Okay.
Which is like
So when you define cross ratio in
you,
3D, do you take lines or do you take planes?
yeah. This is like bit of projective transformation theory. You can read on like Google. I can tell you some handouts if you want. So like there's RJ's handout on projective and there's some one more handout I will share, which cover projective transformation nicely. The projective transformation is completely different thing with
So,
like more
so in,
projective things.
so in
Yeah.
3D, cross ratio is defined with respect to planes or cross ratio is defined with respect to lines?
It's defined with respect to lines, basically.
Okay, because in 3D, won't you have to take intersection of plane and plane to get line?
What do you mean?
okay. I just want to say
And
something. So I'm sure
yeah,
all of us are having like a lot of fun. I am as well, and we want to extend this. But I think like there's another class that Om is going to take, so we can all request him to take it on an extension of this if that's okay with him. Because
Won't
I'm
that take Won't that
Wait.
people cover less amount?
We can have something where Ohm does like double, triple inversions and then homographies and stuff.
Why don't we just do this on live chat on live solve? Can we do this on live solve in Discord?
Sure,
Right
sure,
now?
sure. Why not? I mean, as long as Ohm is free.
Yeah, are you free?
Wait, what are we trying to say? What are you guys want to take?
Extended class right now. Live solve.
Class like extended, like more problems.
And
basically.
more definite, more theory based.
More theorems. Okay, we can do what? Wait. Oh, yeah, we have 28th, where I'm taking class on 28th also. But yeah, that will actually cover like harder problems.
Yes, yes. So right now we
So wait, should we do what or what?
I vote for sleeping this night.
Oh, what is
Because
the time?
if we extend this class, we probably won't have to sleep. And we probably won't be able to sleep.
most
Oh yeah,
people
like
sleep
how much?
after work.
I don't think like
You have
okay.
free time?
Wait, imagine sleeping. Yeah, sleep at. Wait, let me think. Okay. First of all, like either way, if we extending, let's just take 2 minutes break for drinking water. So respect for water there.
Wait, also, I think you should stop recording. Still recording.